Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about some important considerations for probabilistic modeling and forecasting, which we are going to illustrate using a cartoon version of the United States presidential election. You may have noticed that I already posted a video on this topic with the same title a while back. The reason why I'm recording this video again is that in that other video I had made a silly mistake. For those of you that are starting to study data science, hopefully this will comfort you if you feel a little bit confused, because even people that have been studying or even teaching this material for quite a long time can make mistakes. For those of you that are experts in data science or have more experience, this may encourage you to not be too complacent, because we can all make mistakes. Let's get to it. We're going to talk about how not to predict an election. Our motivation is that in probabilistic modeling, on the one hand, we need independence assumptions or conditional independence assumptions because of the curse of dimensionality. But on the other hand, ignoring some important dependencies can be completely catastrophic when we're forecasting or doing some other kind of probabilistic modeling. In order to illustrate this, we're going to focus on forecasting the United States presidential election. This is an indirect election, which means that citizens choose electors that are in the electoral college, and then those electors choose the president and the vice president. There's a number of electors assigned to each state, which depends on the members of Congress that are assigned to that state. So in particular, large states such as Texas and California will have more electors than smaller states such as Delaware. Washington, D.C., even though it's not a state, gets 3 electors. All electors in a state are assigned to the candidate who wins that state, except in Maine and Nebraska. In our cartoon election, to make things easy, there's going to be 51 states, which is the same as in the US. We have 50 states plus Washington, D.C., but there's only going to be 1 elector assigned to each state, just to make our life easier. Let's take a look at a probabilistic model of our cartoon election. We're going to represent the result in each state by a Bernoulli random variable, which is going to be equal to 1 if the Republican candidate wins that state and 0 otherwise. We're going to just assume that there's 2 candidates, Republican and a Democrat, which often happens in American politics. Now the election is determined by how many of these guys are equal to 1. If more than 25 of them are equal to 1, then the Republican wins. Equivalently, if this sum, when we're summing all of the states won by the Republican, is greater than 25, then the outcome of the election is that the Republican wins. We want to characterize the probabilistic distribution of this sum in order to forecast the election. I do want to point out that if we had an election where there's more than 1 elector in each state, then here we would have to multiply this by the number of electors and then see what's the probability that the Republican gets more than half. This would be what we would do if we were trying to forecast the real United States election. So now if we want to compute the probability that this sum is greater than 25, then we need to characterize the joint PMF of the result in each of these states, in the 51 states. That sounds easy, but when we look at it a bit more closely, it's not so obvious, because what's the number of entries in this joint PMF? How many numbers do we have to estimate in order to estimate this joint PMF? Where each of the states can have 2 possible values, so the number of entries is going to be 2 times, because there's 2 values for the first state, times 2 times 2, 51 times. So it's going to be 2 to the 51, and because it has to add up to 1, there's 1 entry that we're not going to need to estimate. We can just do 1 minus the sum of the remaining entries. In any case, this is going to be 2 to the 51 minus 1, which is greater than 10 to the 15. In other words, if we want to estimate every possible dependency between 51 random variables, even if they just can have 2 possible values, that explodes exponentially. We're never going to be able to estimate all of these parameters from data. That's absolutely impossible. We need to make some independence assumptions. This is an instance of the curse of dimensionality. Now imagine that we decide that we're going to model the states as being independent from each other. Now, what do we need to estimate to characterize the joint PMF? Well, we only need the marginal PMFs, because the joint PMF under this independence assumption is going to be a product of all the marginal PMFs. And that makes our life much easier, because we only have to estimate 51 parameters, which is much more tractable. So a reasonable plan is to estimate the marginal PMF of each state. In other words, predict what is the probability that, or determine what is the probability that the Republican candidate is going to win in each state separately, and then aggregate that into our final estimate. And this general strategy is often used when forecasting real elections. Now, in our toy model, the probability that the Republican candidate wins state I only depends on the rural turnout, which we represent by a random variable Ri. This is the fraction of rural voters that go to vote that day. This is inspired by the fact that rural voters tend to support Republicans more than Democrats. It also is inspired by the fact that when predicting an election, interestingly, it's often much more difficult to predict who is actually going to turn out to vote in a particular region, rather than how many voters of a certain, like how many Republicans, what's the fraction of Republicans in a certain region, may be much easier to determine than whether those might be much easier to determine that the fraction of those people that are actually going to turn out in the election day to vote. And that's why when asking people in polls, there's often a question which is, are you sure you're going to vote? Are you completely sure you're going to vote? Maybe you will vote, maybe you won't. And some forecasters just use people who are very, very sure that they are going to vote. Anyway, so in our cartoon example, the probability that the Republican wins state I when the rural turnout is equal to R, this is a value that is going to be between 0 and 1, is given by this formula. It's 0.6 times R plus 0.1 times 1 minus R. Notice that when the rural turnout in that state is equal to 0, then this is equal to 0, and we're left with 0.1. So the probability of the Republican winning when the rural turnout is very low is also very low, okay? Because rural voters tend to support the Republican. When the rural turnout is very high, 1 or close to 1, then the probability of the Republican winning is in that state is going to be 0.6, so even higher than 0.5. So they have a very good chance of winning. Here is where I made the mistake in the previous video. Instead of saying that this was the probability that the Republican would win conditioned on the turnout, I said that this was actually the fraction of rural voters that would go to the election. And that is completely wrong. And this is such an important point that I want to make a little detour to emphasize it. So it's very important to realize that the probability that a candidate wins a state is not equal to the fraction of voters that support that candidate in that state. To make this very clear, let's look at another example with real data. So this is a real poll from Pennsylvania in the 2020 election. In this poll, 281 people intended to vote for Trump and 300 intended to vote for Biden. The fraction of Biden voters is actually pretty close to 50%. It's 51.6%. Now let's take a look at the probability that Biden wins in Pennsylvania according to this data, under the assumption that the data are truly IID, which is never the case in real polls, but let's imagine that that's the case. We're going to use a Bayesian parametric model. If you want more details on this specific example, take a look at the video on Bayesian parametric modeling. But basically what we want to compute is the posterior PMF of the fraction of Trump voters given the data. So we model the fraction of Trump voters as a random variable, and we ask ourselves what's the probability that that random variable is above 0.5. And using a pretty reasonable prior, in this other video where we talk about this in more detail, we look at what happens with different priors, but let's say that we use this pretty reasonable prior on the on the fraction of Trump voters, then what happens is that 78.3% of the time when we look at the posterior after conditioning on the data, this probability is below, this fraction, is below 0.5. So that's the probability, according to our model, that Biden wins in Pennsylvania. That probability is 78.3%. It's much, much higher than the fraction of Biden voters. In fact, what it really depends on is in the number of data points. If this number of data points were lower, then this probability would be lower because, there would be more uncertainty about what is the actual fraction of Trump voters. If this number of data points was much higher, like let's say 1,000 or 10,000, then this would become much more peaked and the probability would be much higher, but the fraction of Biden voters would still be just barely above 50%. So hopefully that makes sense. And this is the silly mistake that I made in the previous video. Let's go back to our cartoon election. So in our cartoon election, the probability that the Republican wins based on a certain, conditioned on a certain value of the rural turnout is this. Now, we're interested in the probability that the Republican wins each of the states. In order to compute that probability, we want the marginal probability of this random variable that represents, this Bernoulli random variable that represents that the Republican wins in that state. And here we can just apply the law of total probability applied to the chain rule. So you might want to review the video on discrete and continuous random variables, but there we show a chain rule which says that this product is actually equal to P of Si at 1 times F of Ri given Si R1. And now realize that if we integrate this with respect to R, then this does not depend on R, and this conditional PDF is going to integrate to 1. So maybe it was clear to you why this equality holds, but this was just a quick justification. It's based on the chain rule for discrete and continuous random variable, because this is going to integrate to 1, then this guy is exactly equal to this guy, so we have the equality. Hopefully that didn't confuse you more than it clarified. But basically we have to do that integral, so we need the PDF of the rural turnout. In our simplified example, we're just going to assume that it's uniformly distributed between 0 and 1. Okay, the rural turnout in each of the states is just this random variable that is uniformly distributed, has a density that is uniform between 0 and 1. Therefore, this is just equal to 1, and we can integrate the conditional PMF, which is equal to 0.5 R plus 0.1. When we integrate this between 0 and 1, this is just going to be equal to 0.1. The antiderivative is R squared divided by 2. From 0 to 1, that's just 1/2. So the probability that the Republican wins state I, according to our assumptions, is 0.35. So not higher than 0.5, but not super low either. Now we want to aggregate all of these probabilities to produce a forecast for the whole election. What's the probability that the Republican wins the whole election? Where under our assumptions, these guys are Bernoulli random variables with parameter 0.35. They're all independent, and we're interested in the sum, which is basically how many of these random variables are equal to 1 at the same time. You could think of this as if we were flipping 51 coins and wanted the probability that more than 25 are heads, where the probability that each of the coins is heads is 0.35. This might sound familiar because the distribution of this sum is just a binomial with parameters equal to n equal to 51 and theta equal to 0.35. And if we want the probability that this binomial is greater than 25, well, we just need to take its PMF. Remember that this term here is just the probability that you see I heads out of 51. And then this term here to the left is in how many ways this can happen. We add them because they're disjoint events. This is just a little review of where this formula for the binomial PMF comes from. But the point is that we have to sum the PMF from 26 to 51, and that gives us the probability that the Republican candidate wins the whole election. That probability is 1.4%, so very low. This is an illustration of our result. This is the PMF of the binomial. The Republican wins if we are above 20, if we are above 25, and that happens with small probability, 1.4. Why? Because even though the probability that they win in one of the states is not that low, it's 0.35, the probability that it happens in enough of the states at the same time, given that they're independent, is very low. So great, we have a forecast for our election. So what could go wrong? Well, the problem is that we have made very strong independent assumptions. And this cartoon example is actually inspired by the 2016 election, where Hillary Clinton was predicted to win in quite a lot of the states, and assuming not too much dependence between the states, this translated to a very high forecasted probability of her winning the whole election. As we all know, that turned out to be wrong. So let's see what can happen when we make very strong independence assumptions in a model, but they don't hold. Here is a fictitious ground truth for our cartoon election. Imagine that the rural turnout is actually highly correlated. It's very dependent, like whether rural voters go out to vote in Wisconsin is highly dependent with whether rural voters go out to vote in Illinois, as may be the case actually in practice. We're going to take this to an extreme, and we're going to make the rural turnout the same in every state, just to make things easier. So probabilistically, now we have a single random variable that represents the rural turnout instead of 51 separate random variables. This random variable is going to have exactly the same marginal distribution as those individual 51 random variables before. It's going to be uniform between 0 and 1. And the conditional probability for each state is going to be exactly the same, except that now they're conditioned on the same random variable instead of on a separate random variable for each state. If we compute the probability that the Republican wins each of the states separately, we are actually going to get the same result, because the marginal, actually this should be f of r, the marginal of the rural turnout is exactly the same, and the conditional probability that the Republican candidate wins based on the rural turnout is exactly the same. So when we compute this interval, we're still going to get 0.35. And again, I made a small mistake here. We are conditioning on the same R. There's not a separate R now for each of the states. So the probability that the Republican wins in each of the states is still exactly the same as before. Completely the same as before. But now let's say how we are going to forecast the whole election. We want the probability that the sum of all the states is greater than 25. Now this sum is no longer a binomial because each of the states are not independent Bernoulli random variables. So instead, we have to consider the conditional probability that this sum is greater than 25, given that the rural turnout is fixed at R, and then we have to integrate this over all the possible rural turnouts, weighting them by the density. This density is still 1 between 0 and 1, so we're going to end up with the following formula. The density is, just to be clear, the density is 1 between 0 and 1. Now this, once we fix R, is indeed a binomial for that specific value of R, so we can plug in the PMF of the binomial there, summed from 26 to 51. So here we have plugged in the PMF of the binomial summed from 26 to 51, following exactly the same argument as before, except that now R is still a parameter here and we have to integrate it from 0 to 1, weighted by its density, which is equal to 1. We can actually do this. I mean, this is a well-known integral for which we could kind of look up the answer, but imagine that we didn't know how to compute this integral, which looks very, very complicated. What would we do? Maybe I have this question here. What if we don't know how to compute this integral? How do we get our final forecast? Well, what we would do would be to use the Monte Carlo method, and this is used all over the place in forecasting when things get slightly complicated, which is always the case in practice. So what we're going to do is we're going to simulate n elections. We're going to generate the rule turnout R according to our probabilistic assumption, which is that it's uniform between 0 and 1. Then we're going to generate the result in each state conditioned on R, following the conditional PMF that we saw before. And then we're going to check what candidate wins. And then our probability estimate is going to be the fraction of times each candidate wins. This should give us the same result as the formula, because the formula is the probability that this happens. And the Monte Carlo method, if we manage to simulate this random variable, the Monte Carlo method allows us to approximate this probability by just simulating it many times, simulating the corresponding random variable many times, and just computing the empirical probability. So again, this is what is usually done in practice. If we apply this to our problem, oh, and by the way, many real elections, for like the forecasts of many real elections, follow exactly this same procedure, except that the assumptions are much more complicated and there's many more variables. But at the end of the day, they simulate what happens in the different states and then aggregate them to see who wins the election many times to produce an empirical probability that is finally the prediction of the probability that a certain candidate is going to win the whole election. So if we do that in our case, this is just to show you what happened before with independent turnouts, where there was a different turnout in each state. The probability that the Republican would win is 1.4 because it was very unlikely that all the turnouts would be high at the same time. But if the rule turnouts are very dependent, when they're high for all the states. So this suddenly boosts the probability that the Republican wins to 20%, precisely because all the turnouts are shared. When the rule turnout is high, the Republican candidate is more likely to win. And because it's happening in all of the states at the same time, then they're also more likely to win the whole election, in stark contrast to when the turnouts are independent. And again, this is a cartoon version of what happened in 2016, where Trump was better than expected in a lot of states at the same time, which indicates that there was some dependence between those states that was not taken into account in the forecasting models. And what have we learned? We have learned that in probabilistic modeling, we need to make independence or conditional independence assumptions. It's impossible to model all the possible dependencies between the 50 states and Washington, D.C. when we're trying to forecast the United States presidential election. But we have to be very careful what dependencies we don't include in the model, because ignoring some dependencies can be completely catastrophic, as illustrated by the forecast for the 2016 presidential election. And that's all I got. Thank you very much.